All right. So our first notes we're going to take are on vectors and scalars. And we're going to start out with a really simple question. What is 2 plus 2? And we're going to say, well, 2 plus 2 is obviously 4, but is it always? So we're going to have an example. We got a student walking 2 miles north and then walks 2 miles east. So is that 2 plus 2 equal to 4? And if it says the distance he has walked, well, he walked 2 miles. Then he walked another 2 miles. And that gave me a distance of 4 miles. So yeah, 2 plus 2 did equal 4. But what if I ask it this way? What is his displacement? Displacement is position relative to his starting point. So if I kind of sketch this out, he went 2 miles north, then turned and went 2 miles east. And now his displacement is going to be where he is relative to his starting point. So up here. And that's obviously not going to be 4 miles. So we'll label that displacement. And for now, we're going to call that D. Well, how are we going to find it? Well, it turns out that north and east are at right angles. So I got a right angle in here, and I can just do the Pythagorean theorem. So I'm going to do it in some detail here. I wouldn't necessarily show all this detail from now on when I'm doing the problem. And you don't have to show all the detail either. You have to show like how you started the problem and just the answer. But I'm going to show all the detail. So 2 squared is 4. 4 plus 4 is d squared. 8 is d squared. Take the square root. Now in math class, they'd say leave it as the square root of 8 because that's exact. But in here, I'm going to have a feel for how big this is. How big is it compared to those 2's? So I punch in my calculator and I get the square root of 8 is 2.83. Actually, on my calculator, I get 2.828 and a bunch of decimals after that. I'm just going to round it to 2.83. And in physics class, we're not that concerned about significant figures like they were in chemistry. So you can round it to a reasonable number of significant figures. If you wanted to write 2.828, that would be fine too. Okay, we don't take off for the number of significant figures. We do take off if you don't put a unit. So I need to know that the displacement is 2.83 miles. And that makes sense because, and that's why I don't like just leaving it a square root of 8. I know it's going to be more than 2, but it's going to be less than 4. So that falls between them, so it makes sense. Now, we're not quite done because that doesn't fully describe his displacement, right? He is 2.83 miles from here, but there's a whole circle of points that are exactly 2.83 miles from that point. We have to describe this point exactly. Now, in this case, it's pretty easy because it's halfway between north and east because these are equal. So we can just say his displacement is 2.83 miles northeast. I have to put the direction as well. So in this example, up here we found distance. And distance is a scalar. Scalars are quantities which have only magnitude. And magnitude is just a fancy word for size. So this just has a magnitude of 4 miles. Okay, and so they're just normal numbers. All the numbers you've been dealing with all your life are just scalars. Now, displacement is what's called a vector. They have both magnitude and direction. So the magnitude of this is 2.83 miles, and the direction is northeast. You have to have both of those. And when we're dealing with vectors, we can't just add the numbers. I can't just say 2 plus 2 is 4. I have to figure out what it's going to be. And when we represent vectors, they are represented as arrows. And the size of the vector represents its magnitude. So I made these about the same size because they're 2, and then this one's a little bit longer. Okay. On to the next page. All right, so we got a little practice here, okay? Now this says, in the space below, from a common origin sketch, okay? So I don't have to do this exactly, okay? The following vectors. Oop, I made a little mistake here. This should be A, and then B, and C. All right, so the first one, it says 20 meters west. So I'm going to put a little dot here. It says from a common origin. And I'm going to go 20 meters west. All right. Now, B is 40 meters north. So I want to make a point straight up. And it should be twice as long as that vector. So again, I'm not really measuring it out, but I have to make sure that it's approximately right. And then 25 meters, 30 degrees north of west. What does that mean? Okay, it's not exactly northwest. Northwest is halfway between. That would be a 45-degree angle. When I write it like this, the second thing is my reference. So my reference is west. I'm going to be 30 degrees north of that. So I imagine something going west. I'm going to go 30 degrees north of it. 30 degrees, 45 is halfway. So 30 would be, not halfway up. And to make it 25, it has to be a little bit longer than the 20. So now I've represented all three of those vectors. Now, when we're going to add vectors, and this won't make sense till we've done it, but we're going to sketch it, we have to move the vectors tip to tail. I'll explain what that means in a little bit. Then we draw the resultant. Resultant is the sum of the vectors. Okay, from the origin to the tip of the last vector we drew. If it's possible, we're going to determine the exact magnitude and direction. Okay, if they're all oriented north, south, east, or west, we can use Pythagorean. If we can't determine the exact values, okay, we're going to estimate it. So here is our examples for that. So we have two forces. So forces are a push or a pull, and they have a direction. If I pull you left, that's going to be different than if I pull you to the right. And the two are 20 and 30 newtons strong. Newtons is the unit for force. And then I want to find the resultant force. Okay, so they're both pointing east. So I'm going to draw these. Here's my origin, or my object I'm pulling on, actually. And I have a 20 and a 30. Now, when I think of a vector, this end is its tip, and this end is its tail. Okay, tip is the pointy end, tail is the other end. Right now, these are tail to tail. To add them, I have to make them tip to tail. So I'm going to redraw it. So I'll draw my 20. Now I'm just going to take this 30 and I'm going to slide it over so its tail is at the tip of the 20. So I'm going to move it over here. So these are tail to tail. You don't even have to write this out. I'm just doing it so that you can see what I'm doing. And then the resultant is from the origin to the tip of the last vector you drew. So there's my resultant. I'm going to label the resultant R for now, and that is going to be 50 newtons long. So it would be 50 newtons. East is my resultant, because remember, vectors have to have direction as well. So just saying 50 newton is not complete. That's just the magnitude. I have to have magnitude and direction. And be careful, N doesn't stand for north. It stands for this newtons. My next one, 20 newtons east and 30 newtons west. So 20. Now I'm going to jump ahead. No, I'm not. And 30 this way. Okay, they're tail to tail. All right. The 30 is going to win. And when I redraw it tip to tail, I'll have my 20 here. 30 has to be longer going the other way. I draw from the origin to the tip of the last vector I do for my resultant. So there's my resultant. Well, how long is that going to be? It's going to be 10. So my resultant is 10 newtons west. All right. Now, if the things are acting in the same direction, I can just add them, right? I wouldn't have to go through all this if I realized that. If they're in the opposite direction, I just subtract them, and the resultant always ends up being in the direction of the bigger one. Now, here's where it gets a little bit more tricky. 20 east, and then 30 north. Ooh. Now, I skipped ahead. I actually drew these tail to tail. All right, I really should have done this. And let's think about this. If there's an object here and somebody's pulling it 30 this way and 20 that way, I'm going to end up going off this way somewhere. okay? To know exactly where, I take and I slide the 30 over so they're tip to tail, and then there is my resultant. And remember, you always draw it from the origin to the last vector you just drew, to the tip of the one that you moved. Now, how am I going to figure out how big that is? This is a right triangle, so I'm going to do Pythagorean. So r squared is 20 squared plus 30 squared. Now, like I said, you don't have to show this all of the time. And I'm just going to do the work on my calculator and get the answer. And I end up with an answer of 30.1 newtons. And that sort of makes sense. When they're working together, I get 50. When they're working against each other, I get 10. Well, this resultant, they're not working together to give me a total of 50, but it's bigger than 10. Okay, so there is my resultant. Now I also have to figure out the angle. And here's where we're going to have to do a little trig. And this is about as hard as a trig you're going to have to do all year. So don't get too panicky. All right, but I got to find that angle down there. And to do it, I'm going to say this is my opposite side, this is my adjacent side, and this is my hypotenuse. Okay? And I'm going to use opposite and adjacent because those were kind of the givens. This was an estimate. Remember, I rounded that. So this isn't as exact. So if I think of SOHCAHTOA, and again, you don't have to show all these steps. Okay, I probably won't after this. Okay, but if you're rusty on your trig and you have to write SOHCAHTOA down every time, feel free to do so. All right, and I have the opposite and adjacent. So I get tan of my angle is opposite over adjacent, TOA. So tan of my angle is equal to 30 over 20. Tan of my angle is 30 divided by 20 is 1.5. And how do I get, if I have tan of the angle, how do I get the angle? I have to do the opposite of tangent. So theta is going to be tan minus 1 of 1.5. And that's going to give me theta equals. And I punch that in my calculator, and I get 56.3 degrees. All right. Now, to completely write this out then, I would say R is 30.1 newtons at 56.3 degrees. And how am I going to describe that? Well, see how here's east. This is going straight east, and then I'm swinging north of it. So I'm going to say north of east. I can't just say northeast because that means exactly a 50 degree or 45 degree angle. Now this last one, we're not going to be able to get the exact value. We're going to estimate it. So we got 20 east and 20 degrees north of east. Now 20 degrees is a pretty skinny angle, so I'm going to make it pretty small angle. And I'm going to write in there that that's 20 degrees, and I write this as 30 newtons. Now, they're tail to tail, so I have to move them so they're tip to tail. So now I just take this 20 and I slide it over here, but it has to point the same direction. It has to be parallel. And I'm going to say that this is 20 degrees. Okay, so now I've moved the 30 over there. Okay, now my resultant goes from the origin to the tip of the last vector I drew. So something like that. Resultant. Okay, now like I said, we can't actually find this exactly yet, so we're just going to estimate it. But if they were directly on line with each other, that would give me 50. It's pretty close to that. So I'm going to estimate that R is going to be maybe 45. All right. Now, if you have anything from, it's obviously bigger than 30, so maybe you said anything from 40 to 50, I'd give you kind of credit for that. And for my angle, I'm going to measure this angle right here. It looks to me to be about half of that 20. So 10 degrees north of east. And again, it's north of east because I'm looking at east and I'm swinging up this way, and it looks to me like it's about 10 degrees. So that is the beginning of our motion unit.